Alright guys, welcome to the second VOD of Unit 3. Today we're going to be discussing the periodic table, the elements on the periodic table, and the groups and families that exist on the periodic table. So lots of information and probably a little bit of a longer video, probably longer than what you become used to. But all this information is tested, so it's important that you do pay attention and take thorough notes throughout this process. So let's kick things off discussing the periodic table's geography, okay? Now, as you can see from this image down below, the boxes on the periodic table contain particular elemental abbreviations, okay? So a shortened handle, if you will, for what the element is. For instance, the one in the picture is phosphorus, and it's given by P. Silicon and sulfur are also there, silicon with Si and sulfur with S. Okay, now each element on the periodic table has a different one. Most of them don't get any larger than 2 letters. The ones we continually discover might tend to have 3. Okay, now inside of this box there's a lot of other information. As you can see on the phosphorus box, there's a big number 15 up at the top, okay? And that 15 is its atomic number. Okay, remember from middle school that the atomic number is equal to the number of protons within the nucleus of an atom. Okay, now that atomic number is also equal to the number of electrons, okay? So A is equal to P is equal to E, or ape, okay? We discussed that in the last class, but a little more thoroughly. Now the atomic number is contained within the box for all of the elements on the table. The atomic mass is also contained in here. Now, the atomic mass that it gives you for phosphorus in this example is probably a little bit large, but usually they're around 2 to 3 decimal places after a bigger number, okay? Now, the atomic mass tells you the mass of the nucleus of the atom, okay? So that is where the majority of the mass is contained for the atom, once again, is inside the nucleus, and that is the protons and the neutrons, right? So to find the number of neutrons, again, remember we take the atomic number and the atomic mass. We take the atomic mass and then subtract the atomic number to leave you a number of neutrons, okay? Don't forget that, because that's going to hang around and it'll be tested on your exam. So we also have a little bit more thoroughly, okay, we have the atomic number and atomic mass. As I told you before, the majority of it is contained within the nucleus of that atom. So for instance, we have a Bohr diagram of uranium over here on the right. And as you can see, the 92 protons and 146 electrons are contained within the nucleus. Okay, now, so the reason that this atomic mass can get so high is because the number of protons and the number of neutrons are kind of equal in terms of mass, all right? Now, the electrons don't really count because they're 1/1850th, so infinitesimally smaller than the protons and neutrons. So we don't really add them into the atomic mass. Okay, remember the atomic mass is an average of all the isotopes of that particular element. So we'll discuss that a little more in depth in class, okay? Now, how are elements arranged on the periodic table? They are today arranged by atomic number, or the number of protons within the nucleus, okay? They're all arranged by 1, 2, 3, 4, etc. Now, whenever Dmitri Mendeleev first started building the periodic table and constructing it in his own way, they were arranged by atomic mass, and it was a lot more sloppy than what you have now, okay? You had elements all over the place, hydrogen was in with lithium, and it just turned into a giant mess. But that's not how it is today because of work from other scientists, okay? So, on the periodic table, it is highly organized based on the fact that it has different periods and different families, or groups, okay? Now, the periods run horizontally, and the families run vertically, okay? Now don't forget that, because that'll get way more important when you get into chemistry, especially the periods, but the groups are vital for IPC, okay? We need to understand what each group is and their valence shell activity in order to understand why they do what they do, okay? So the families contain similar characteristics, okay? They all react the same, they all have similar melting points, boiling points, and physical and chemical characteristics, like what we discussed last unit, all are contained within the similar elements in the families because they all have similar valence shells, which we're going to talk about way more in depth. So, once again, we have valence shells that are similar in the families. The first family has 1, 2, 3, 4, 5, 6, 7, and 8, and so on, okay? Now, in the middle, we have the transition metals, and the transition metals kind of have variable valence. Sometimes they have more, sometimes they have less. But for the most part, the metals on the left and the nonmetals on the right side of the periodic table both have very similar characteristics of their valence shells by their family. Okay, that's why they're arranged the way they are. So what are metals, nonmetals, and metalloids? All right, metals are lustrous and good conductors. That means they're shiny and they definitely conduct electricity. Don't forget that, right? The ability to conduct electricity or conductivity is the ability to pass current through it. Metals are contained on the left side of the periodic table. Nonmetals are poor conductors. They're brittle solids if they do exist as solids. Sometimes they're not. Most of the time they're gaseous. Okay, they're contained, the majority of them, on the right side of the periodic table. The metalloids are your in-betweeners, and they make good semiconductors because sometimes they do have good conductivity, and sometimes they don't. It depends on how they act. Sometimes they act as metals, sometimes they act as nonmetals, okay? So silicon, which is a metalloid, acts a lot like a nonmetal, whereas aluminum acts a lot like a metal, okay? You see the difference there? They're both contained in similar families, but they act very differently, and they follow that zigzag line on the periodic table that you can see right here. Okay, once again, aluminum, silicon, they both are along the range of being metalloids, yet they both act very different. Now, we have very different periodic families, and they range from heavy metals to all the way to gases, okay? So we'll start off on the left side of the periodic table and work our way across, okay? So group 1 on the periodic table is known as the alkali metals. And this is lithium, sodium, potassium, rubidium, cesium, francium, okay? We're going to do sodium demonstrations in class and kind of get a feel for what that stuff likes to do. They all have one valence electron. That's important to note, okay? Now, what is a valence electron, right? Remember from last unit, or last video, when we discussed that the valence electrons were the electrons left in the outer shell of a boron model, okay? Now, in the case of alkali metals, they like to give that up. They like to form +1 cations. Remember, cations are positively charged ions. Okay? Now, like them, the alkaline earth metals are group 2. Okay? That's beryllium, magnesium, calcium, strontium, barium, and radium. Okay? Now, the bottom two on these, francium and radium, are kind of radioactive, so we won't really ever mess with those, but the other ones are really interesting. They're highly available readily throughout the world. Okay? Now, alkaline earth metals are group 2. They are as highly reactive, slightly less so than the alkali metals, but they like to form +2 cations, okay? They like to give up the 2 electrons that are in their valence shells, okay? So, they like to get positively charged, okay? Remember the octet rule, where all the atoms wanted to have 8 electrons in the outer shell. The reason that these two families like to give up their electrons is because they want to have 8 electrons in their valence shell too. They don't want to be different. So they will readily give up that electron so that they can become like the noble gas before them. We'll talk about that here in just a second too once we get to the noble gases, all right? So just remember, alkali metals form +1 ions and alkaline earth form +2, okay? Now, +1, the alkali metals, is the most reactive metals on the periodic table, okay? They will readily give that electron up. They don't want it, okay? Now, the reactivity kind of decreases as you go across the periodic table, but these guys, lithium, sodium, potassium, etc., really want to get rid of that electron, okay? Don't forget that. Now, we get into the nitty-gritty, the nonmetals and the metalloids. First, we have the boron group. It's group 13, and it's not really highly reactive, okay? They will donate their electrons, and they tend to be found as +3 cations. So these elements have have 3 electrons in their valence shells, and they will readily give them up, but it takes a lot of effort, okay? So they're not as highly reactive as the alkali and alkaline earth metals, okay? So that will bring us to the carbon group, which is group 14, and they're really not reactive, okay? These are almost inert. You have to try really hard, and they tend to be more organic compounds, okay? Especially carbon. The entire basis of organic chemistry is all about the chemistry of carbon. So this is an organic molecule, or sorry, an organic element that doesn't really react, and that's a good reason for it being able to support life, okay? That's what organic elements are. So this is group 14. They will either give up all their electrons, or they'll take on 4 more. They're going to try to covalently bond, which we'll talk about later. to get a full valence shell rather than just give everything up at once, okay? So carbon's where things get where everything kind of falls off the range in terms of giving up electrons or taking on electrons. Now, after carbon, we'll see that reactivity come back. And so we get to the nitrogen group, which is also known as the pnictogens, okay? This is group 15, all right, and it generally accepts electrons. They want to be -3, okay? They have 5 electrons in their valence shell. They want that octet, or 8, okay? So they'll take on 3 more so they can go ahead and get it. Nitrogen, phosphorus, arsenic, antimony, bismuth, and that other one down there, which is radioactive and one of the newer elements. So nitrogen and phosphorus are very frequent around us. Nitrogen especially is one of the organic molecules, okay? It exists in all the air that we breathe, so it's all around us all the time. Remember that this is group 15, okay? Now, again, nitrogen, phosphorus, and all the ones below it all share that 5 electrons in the valence shell thing, okay? Now, oxygen, on the other hand, oxygen, once again, has 6, okay? These are a little more active. This is called the chalcogen group, okay? They like to gain their electrons. They are a little more reactive, but they are nonmetals, okay? So, whereas we had the alkaline earth metals that were very reactive metals, we have this chalcogen group that is a semi-reactive non-metal, okay? Keep that stuff in mind, and we do also have the metalloids running that zigzag down it also. But they want to gain those 2 extra electrons, and they are known as group 16, okay? They're the chalcogens, oxygen group. That's probably what you'll hear them as, or what you probably have heard them as. Now that brings us to the last 2, okay? Now we have the halogens, which is group 17. They are highly reactive nonmetals. They are the most reactive of the nonmetals, okay? They really want that extra electron so they can be like the noble gas on their right, okay? So they're guaranteed going to take on an extra electron to have that -1 charge, okay? Noble gases are the last group, okay? That's helium, neon, argon, krypton, xenon, radon, and unoctunium, but that unoctunium is once again a newer element. The main ones that you'll always hear about are helium, neon, krypton, and argon, okay? And xenon too. Radon's radioactive, so we don't really like to mess with it. But helium doesn't have that full octet. However, in its first shell, it has 2 electrons. Remember that in the Bohr model, the 2 electron shell means that it's full, okay? So technically, its valence is full. Does that make sense? You'll learn a lot more about why that can work whenever you get into chemistry. Neon, argon, krypton, xenon, radon, etc. All have that full octet. And as I said before, the metal that follows the noble gas in the next period tends to be active to become like the nonmetal before. So, for instance, sodium really wants to be like neon, so it'll give up that electron. Okay, and fluorine really wants to be like neon too, so it'll take on an electron, okay? So we tend to have give and take of electrons between the halogens, the alkaline metals, the halogens, the alkaline earth metals, and even the chalcogens and the alkaline metals and alkaline earth metals, okay? You see that trade-off of their electrons. So they tend to form ionic bonds, which we'll talk about more in the next VOD. But for the most part, all of the trends of the periodic table work because the families, like the halogens, the noble gases, alkaline earth metals, pnictogens, alkaline metals, etc., all have the same number of valence electrons, okay? So, again, fluorine has 7, all of the noble gases have 8. Because the noble gases have 8, they don't really react. They're called inert gases, which means they don't react. They satisfy their octet. Now, all the rest of the elements on the periodic table want to have that octet, so they're going to take on or give up electrons so they can be just like the noble gases, all right? So don't really forget that stuff. It's going to come in handy for the next couple of labs. If you have any questions, again, come in for activity period or post them in the comments section below, okay? You guys have a great evening.